methyl, we did that, ethyl, propyl, and he says that used to be called N-propyl because you connect to the middle one. Now you call it isopropyl. Iso is a prefix that they toss in to mean branch, and that's the only reason I wanted to look at this slide. Here's butyl, which is a normal 4-carbon. I don't know if I put that many into a molecule because I have to count the darn things. Okay? And the longer I have to sit there counting, and sometimes people write, I don't know what they write, I have a hard time counting to see. Okay, so that's butyl, but there's isobutyl. The only thing I wanted to get to down here, there's the T-butyl group. I don't think I'll use any of these, but these are things you see as substituents for the different things that are put into hydrocarbon chains or elsewhere. Notice the tertiary, it looks sort of like the tertiary thing we saw with the alcohols. Except there we have an OH group and a bunch of carbons, and here's the secondary butyl where we have one hydrogen, some methyl groups, some alkyl groups attached to that carbon. I always make a joke about isobutyl. It means a chain, a branch at the end of the chain. This is the IUPAC 4. This is butane. Here's a branch. And they call it isobutane. Now this is in the common system nomenclature, and the only reason I bring this up is because they use that prefix to mean some sort of branch at the end of the chain. Isopentane. What's the common name for this? That's not the name I want to see, but it's isopropyl alcohol. There's no branch here. They have no sense of geometry at all in organic chemistry. In other words, iso means some sort of branch at the end of the carbon chain. There's no branch. This is a zigzag carbon chain with an OH in the middle. But it does have the common name isopropyl alcohol. Okay. So I just wanted to look at some of these different substituents, none of which we will need to use for any of my examples. Moving right along, here are these different ways of drawing these stick structures, or whatever you want to call them. Well, this thing's going to fly away pretty soon. It's that zigzag thing, you couldn't want to use it different places. That's just to illustrate positional isomerism using those sticks. Here's the list of the different functional groups. I put the slide in while we were on a break so we can get through it. And notice we've gone through most of these already. We've done the alkanes, the alkenes, the alkynes, alcohol. Alkyl halides we're going to treat as a substituent. We're just going to talk about bromohexane or whatever, putting it in and locating it. These are the amines. We're going to treat that as amino. We're not going to call it propylamine. That's using amine as the functional group. Okay, so we're going to call it, we're just going to put it into the chain and call it amino. Then there's the aldehyde ketone pair, carboxylic acid ester. This is the table in your book. We're not going to do this, but sometimes people, when I ask them to draw me isomers, try to name this as an amino. That's incorrect. That's a particular functional group where the NH2 has taken the place of the OH, and we call it an amide. Where do you recognize that thing? Thioacetamide. Thio means you put a sulfur here and an NH2. So that's thioacetamide. So it's a functional group all on its own. And here's arenes. That just means You have the aromatic benzene ring, we're not worried about that. And there's the alkylides, phenols. He treats these are all treated as different functional groups, but we're not going any further than what we've done. So we've talked about amines, and we've talked about amides, and that's the distinction. Here he's looking at some properties. Here he's talking about conformation. And there he talks about eclipsed and staggered. Remember, this is ethane. It can rotate. You're going to see this more in organic chemistry. But if you look down this axis here, when they're like this, where they're overlapping each other, they call that eclipsed. It's a higher energy state than when they're off at a slightly different angle. So there is a little energy barrier going from here to here. Okay. And then one of my favorite things. Oops, these are cyclocompounds. Cyclopropane, that's really strange because that's a 60-degree bond angle. The carbons want to have about 109. So what's this likely to do if you're not careful? It's going to blow up. It reacts violently. Okay. This is a little more stable. Once you get into the cyclopentanes, now the only thing here, remember I said you should show all the hydrogens. You just don't leave it like that. There's the C6H6. When we get to cyclohexane, here's another interesting thing in organic. Notice I'm trying to find the interesting things. There's the ring strain. There. There's the benzene ring. It comes in two forms. One, like that, it's called the boat form, where these two carbons at the end of the hexagon are tilted up. This one's tilted up, this one's, he's got it backwards. This is tilted up, this is tilted down. This is called the chair form. This is a lower energy state than that. The molecule flexes when you shine light, a certain frequency of light on it. You can detect that. So those are more interesting things about organic chemistry because you can relate it to some of the things the molecule does. Okay. There's just preparing an alkane. One is you're adding hydrogen to the double bond. That's easy. You're removing sodium bromide. We're not going to do any of these reactions. We'll just talk about them. We'll come to that when we talk about polymers. There's the combustion. If I ask you for complete oxidation or whatever, strong oxidation, I don't want to see CO2 and water as products. You do. That's better than nothing, but I'll still mark it wrong. Okay. Here's some more. Ethylene is the common name, 1-butene. He's just going through some nomenclature on these slides. Isopropyl ethyl and acetylene. We're not going to do anything like that. If we saw this molecule, this is the only name I would accept, unless you want to put the 2 right in here. And then you could break it apart for the Y and E and put the 2 in the middle of the molecule. Hopefully that's the new better way of putting it. So what he's done is in the blue, he has the correct IUPAC names, and then in the dark print, he has the common names that you frequently see. And obviously that last one you're not going to frequently see anywhere. Okay. There's the cis-trans isomer using either the hydrogen or the methyl. Cis means on the same side, trans on opposite sides of the double bond. And that's as complicated as we're going to get. And now we talk about elimination reactions. This is where you have an alcohol and you add something like sulfuric acid, which tries to take out the water. Sulfuric acid sucks up the water. When you do those esterification reactions, you add sulfuric acid as part of the reaction mixture. Again, that's because of the way the things react. Okay? And now you make the double bond. Here's addition. For adding 1 mole of bromine to that double bond, you form the 1,2 dibromo compound. Because bromine is looking for electrons, double bond has extra electrons sitting in there. I'm not going to ask that question. Are you ready? HBr. And I'm going to ask this question, possibly. Because notice, the hydrogen can go here, and the bromine can go here, or, well, here they are, two pictures. Two possible products. You would look at that and say, you should get 50% of this, 50% of that. You do the experiment. Guess what you get? Oh, I'll make this up because I don't think he gives me the numbers. But you get about 70% of this, maybe 20% of this, and you never get 100% organic chemistry. There's always some sort of junk left over. Okay. So you get more of the middle one, less of the second one, and it's called Markovnikov's rule. Okay. Some books spell it with 2 F's. That's because this is from the Cyrillic alphabet and we don't have a corresponding letter there. So we just sometimes translate it as V's, other times as F's. And when I do it, I put 2 F's here and a V here, so I split the difference, or vice versa. I don't care how you spell it. But Markovnikov's rule explains why that happens. And again, when I studied chemistry, it was all very political. And it was the thing where them that have get, and the Satius rule, which we didn't mention with the elimination reaction, them that don't have lose. And the halves mean hydrogens. So this one had 2 hydrogens, this only had 1. So when you add the unsymmetrical reagent, the more electropositive reagent goes here, the more electronegative part of the reagent goes here. We use water instead of HBr. The OH would go here, and the H would go here. So it's an unsymmetrical reagent. Nowadays, we explain that using kinetics and everything else. There he does HCl, it's the same principle. And he adds another mole of HCl. And notice, instead of getting the different distributions of chlorine on all the different ones, this will be your principal species. If you add 2 moles, you only add 1 mole, this is your principal species. The explanation, this is the mechanism thing. I'm just trying to make organic chemistry seem more like a science instead of something where you just memorize it, which is why I didn't really care for organic chemistry. They just said memorize that, that's the way it goes. You know that for the quiz, you'll pass the quiz. You don't know it, you won't pass the quiz. So we have now we're going to add HBr. Okay. Now the bromide is trying to get away from here and look for electrons, and it sees electrons here. It can make this has a positive charge on here. I'll just put a plus. These are the intermediary species. Remember that from kinetics. Or it can make this. Next electron goes this way. These are called carbocations. These reactions are fast. Remember that from mechanisms? So it does this when it comes in, it does this. This is more stable than this. Oops, I put the plus in the wrong place. The electron went this way. Not good. In other words, this is more stable because it can distribute the positive charge over more atoms. This is less stable. So this is the one that when the H plus comes up, it's going to see the extra electron on here and add in here. So now we're doing it in terms of intermediary species, the activated complex, remember that from kinetics? So these are, this one's more stable than this one. That's why you make more of the product where the bromine goes on here and the hydrogen goes on here. Okay, so these are called carbocations, those are the intermediate species. And that explains why we get one product as opposed to the other. Similarly, in the other direction, that explains why, if I was trying to take away a hydrogen here to make water, it would go this way rather than this way, because again, it talks about the stability of the intermediate species. So that's not a rule your book mentioned, and we're not going to worry about it. That was the elimination reaction. But I could ask you to predict what the product was if I add an unsymmetrical reagent to the colored one. And you don't have to do the mechanism for me, but that's what they do in organic chemistry to make it more interesting. So when you study organic chemistry nowadays, you study a lot more about the mechanisms. I'm not going to do that reaction.